Okay, I'm Yasser from University of Leeds, and here I'm presenting some results on the characterization and correction of the InSAR phase bias, which is mainly affecting the short-term multi-loop interferograms. I would like to thank all who contributed to this work, especially Andy Hooper, Tim Wright, Milan, Yumurishita, and Homa Ansari. In general, when we calculate the closure phase using three multi-loop interferograms obtained in three acquisitions I, J, and K, in the absence of the phase bias, this should be zero. However, due to the lack of consistency, this will not happen and we end up to a non-zero phase closure. In this example, you see a 18-day interferogram in the left, and these are the three corresponding 6-day interferograms which are spanning the same time. Subtracting these two, we will come up to this non-zero closure phase. These residuals are product of the multi-looking and are mainly associated with the changes in the soil moisture and in the water content of vegetation. In this animation, you can see how these phase residuals are being accumulated in time. Although the amount of the closure phase is small in each individual loop, its accumulation in time can significantly impact the final estimated velocities, particularly for applications where millimetric accuracies are required. If we plot this in different land covers, the rate of bias accumulation is not steady throughout the year, being highest for some land covers such as croplands and lowest for the urban pixels. And our experiments showed that its pattern matches well with the precipitation season. The mitigation strategies are either trying to correct the interferograms using some physical models, or the phase linking approaches can be employed. These phase linking methods employ the full coherence metrics as their input, which requires the generation of all possible interferograms in the time series and are believed to have the least sensitivity to the phase bias. In this study, we propose an empirical solution to correct for this phenomenon. So the main objective of this research is to develop a bias correction approach that uses just the interferograms formed from the closest three connections. These are the interferograms which are commonly generated by the automatic systems such as the Comet InSAR system. Our observations are the closure phases obtained using 2 and 3 nearest connections, which are referring to 12-day and 18-day interferograms in this study, as here we are testing the method in an area with the Sentinel-1 6-day acquisitions. So if we write in terms of the phase bias terms, we will end up to these equations, and delta are referring to 6, 12, and 18-day bias terms as the unknown parameters. But this is an underdetermined system of equations. So to solve this underdetermined inverse problem, we introduce an assumption that the bias in an interferogram is linearly related to the sum of the biases in shorter interferograms, which are spanning the same time. So using this assumption, we end up to this overdetermined system of equations, and the unknown bias terms can be estimated using a least square inversion. After the estimation of the bias terms, every single interferogram can then be corrected using these equations, as you can see at the bottom. Here are some results. In this plot, the 1-year cumulative closure phases are shown using the original interferograms in the left and using the corrected interferograms in the right. It is clear that correcting the interferograms has significantly decreased the closure phase signal, with the mean value significantly decreasing from about -1 radian before correction to about 0 after correction. And for the validation, we compared the estimated velocities to an eigendecomposition phase linking approach. Here is the scatter plot of the original 6-day estimated velocities versus the velocities from the EPL phase linking in the left, and as it is clear in this figure, it is skewed to the left, which indicates that the velocities for many of the pixels are biased negative before correction. But the scatter plot of the corrected 6-day velocities versus the EPL velocity in the right figure is somehow centered on the diagonal line, which indicates a high degree of correlation between the corrected velocities and the EPL velocity, and shows a dramatic reduction in the phase bias. And finally, this plot shows the differences between the velocities obtained with EPL and those calculated from our corrected and uncorrected 6-day interferograms. And again, as you can see, after the correction, the velocities are much closer to those from EPL. Thank you.